Hi, so I am Heather Nolis, and I am here to talk about speech, the other NLP, where NLP is natural language processing. And I work at T-Mobile. So a little bit more about me. I actually am a machine learning engineer, and I started at T-Mobile in 2017. But before that, I really wanted to get my PhD in neuroscience, and that's how I actually got into programming. I did a study, and I had lots of beautiful microarray data, and they were like, pass it off to the analytics team, and I was like, no, thank you. I'm a control freak. I'm going to learn how to program this and do clustering myself. And so that's how I got into the field of data science at all. And I'm extremely active on Twitter, so you can follow me there. But if you want like a real response, it's much easier to connect with me at work because I tend to take my work communications pretty seriously. So if you want a good response time, my work email is right there. And then just a little bit about what a machine learning engineer does at T-Mobile is my team consists of analysts and software engineers and architects and data scientists and machine learning engineers. And our goal is to build full stack software. And the role of the machine learning engineer is really to work with the data scientists who are actually building the models and get those models working well in the context of the entire software ecosystem. So making sure that they're performant, they are APIs, so that way our data scientists can kind of really focus on the modeling. And so this talk will be focused on a lot of that extra stuff that goes into making data science models run and work at scale. So my team is called AI at T-Mobile, and we really focus on, well, we did focus on customer care messaging. So what this means is that if you have a problem with your phone, you can pull it out and you can text or go to Twitter or go to Facebook or Apple Business Chat and write a message to T-Mobile and have them actually have a conversation with you about the issue that you're having asynchronously via text, which I hate phone calls. And so we were really focused in that world where everything's text messages, it's back and forth, and how can we leverage the context of the conversation to really provide insights to our call center experts sitting there trying to troubleshoot your problem. And we call it AI under the covers. So we don't want to do anything that's flashy and in your face or gets between a customer and the solution that they want. So we're focused on building AI that helps experts in call centers solve problems faster. We're focused on helping the coaches for those care experts measure the impact of the strategic initiatives that they have. And we're really focused on providing self-service for customers like chatbots and things, but only if the customers really want that option. So we don't do phone trees, no persistent or no disclosure chatbots, no creepy monitoring disguised as personalization. We're really focused on making sure that our AI is ethical, disclosed, and tucked away and not stealing the show from the things that really matter, which are customer problems. And so our flagship product was called Expert Assist. And how Expert Assist works is it sits on the computer where the experts are looking at care conversations. And you've all called into care. And so in general, when you call on the phone, you might have to sit in a queue and wait until someone can talk to you. The very same is true in text messaging. So if you text message in, it might be 1 to 2 minutes before an expert actually has a second to get to your problem. So we were thinking, in the time between you've sent us your first message and the time between the care expert gets to look at your account, what cool things could we do that would let that care expert solve your problem quicker? So when you message in and you say something like, hey, I'm traveling to Europe and I need my phone to work, we have about 2 minutes to munch data. And what we do is we classify the topic. And these are using models built in R that are TensorFlow Keras models that are containerized in Docker containers, and that spits out a conversation topic. We also look up relevant internal Wikipedia articles that would help you solve the issue as the care expert. So in this situation, if I didn't know how to unlock a phone, good news, lots of information there about how to unlock a phone. And then we also pull up relevant account facts that would help the expert say, okay, well, it's an iPhone X, and I know this about iPhone X's, and here's exactly how we unlock those. And then the model moves into a real-time situation where it actually slides along the conversation. So if this conversation pivoted and we began to talk about how I really need to pay off my huge bill before I unlock my phone, those things would update in real time. Sub 1 second is how quickly we want it to update. We want it to be extremely responsive and interactive to the conversations that are going on. And so this is a story all about how my boss looked at Expert Assist and said, cool, make it work in voice now. So in this 20-minute segment, just sit right there, and I'm going to tell you how actually the skills needed to deploy and train models in voice are completely completely separate from the skills needed to deploy and train models in text, and the stunning journey of how I learned that. And we had to prove that I could do it in just 60 days, or that our team could produce this product, and we only had 60 days to do it. So my first response when my boss said, take expert assessed, which works in text message, and make it work in voice, I went the scrappiest, easiest, just prove to me you can do it. I was like, this will be super, super simple. All you got to do is send me the sound. I'm going to go out and get Amazon, AWS, Google, Microsoft, some vendor to do speech to text, because that's totally a solved problem. And our models will work very well because they've already been optimized and they're on Kubernetes. So the scale will be fine. So even though voice has 10 times the traffic messaging does, I don't worry about it. And our models will work just fine if I retrain them on voice data. I won't need to restructure or do anything really big as far as the models are concerned. It should be very simple. Literally every piece of this was incorrect. So some other things I got wrong, just to throw them out there. I thought that sending telephone audio to a computer would be easy. I thought that we could have any speech to text product work, and it would make our models, it would be sufficient for our models to perform well. I thought our models would be able to handle a 10 times scale increase with a 10 times container increase. We would have that linear matching without a lot of refactoring. And I thought our models would perform the same. So I thought if you gave us a topic, if you gave us a voice conversation about payment arrangements, our topic model would classify it just as well as if it was a text conversation, which that was all wrong. So I'm going to walk through my major assumptions one by one and tell you exactly how wrong I was. So the first thing I said was just send me the sound, because, you know, that's super easy. And so in my dream, it would go something like this. The customer would say, "Hath thou any BOGO iPhone deals for me? Thanks." And, you know, the network would do its thing. Audio would be converted to text. Our servers would pump it out, and boom, it would just appear on the agent screen. And they would be like, yes, that sounds great. It doesn't work like that. So the first issue we came across is we couldn't get a copy of the voice stream. Telephone architectures are really old and interesting. They are not like computers talk to each other at all. And so we only had 2 copies of the voice stream. One of those was from the customer to the care expert, and the other one was for coaches to listen in and help out if necessary. So that leaves 0 voice data for our models to actually run on. To get our models to run on voice data, we had to install hardware at our T-Mobile on-premise data centers that could create a copy of the audio stream and send it out. This is a millions of dollars, like a multi-million-dollar investment. And installing hardware can take months and months and months. We only had 60 days. So that's the first issue. So if we can get buy-in from stakeholders, we can get millions of dollars, then maybe we can get a copy of the audio, but how can we then get the data to our models? Our models live in the cloud, and the telephone data lives in on-premise data centers. Sending data back and forth takes time. So when you're texting with somebody, if you have to pause for 30 seconds and go and get a drink of water, that's totally okay. If you pause for 30 seconds in a phone call, it feels like you're being ignored. And that's the opposite of what we want to do with the whole AI under the covers thing. We want our artificial intelligence to be unobtrusive. So if our models are ignoring you and our reps are ignoring you because the models are still processing what happened 30 seconds ago, that's not a good experience. You need to be incredibly quick. And then there's the issue that telephones weren't made to talk to computers. Telephones use SIP and RTP streams to actually create telephone calls. So SIP will like do the job of creating the call, and RTP basically sends the audio data back and forth. There's one stream from the caller to the recipient, and then from the recipient to the caller. But computers don't talk like that. Computers talk using text streams and APIs and WebSockets. So basically, it seemed like this was an impossible endeavor. And until we had a realization, which you probably have had because we are all on a video sharing service, and that's lots and lots of people have already solved the problem of how to get telephones to talk to computers. Zoom does it, Skype does it, WebEx does it. Anytime that you can call into a video conference call, they've already solved this problem. So what we did is we leveraged these connectors from Amazon Chime, which is Amazon's video conferencing product, and then Amazon Kinesis streams to actually convert the SIP RTP streams, which is like old school telephony data, to a format that our computers can understand, which is WebSocket audio streams. So great, we're able to buy ourselves out of this problem also. And so when I said send me the sound, I showed you my beautiful flow chart that was pretty linear of how I imagined it going, and it just doesn't look like that actually. How it works is somebody calls in, and that call data goes to the data warehouse. In T-Mobile's data warehouse, it then copies that stream. It sends one stream to the desktop where the care agent is working so they can listen to the call. And then it sends one stream to our public cloud. And in the public cloud, that stream is then sent to our private, it's converted into things that WebSockets and things that computers can understand. And it's sent to our private Kubernetes cluster, which then has to go back out to the public cloud and say, turn on the transcriber. And the transcriber then has to send it back into our private cloud to our models, which can then eventually be delivered to the agent desktop. This is not how it works in text. In text, it's very straightforward. You say a message, you get a result. In this, there's so much cycling back and forth, and each of those little jumps adds a few seconds. So we're looking at a situation where it's even more important that we're really fast, because in voice, you have to be on the ball and you can't have these awkward pauses. But the steps between getting our models results and the customer saying something, there's so many steps between it that it's causing a lot of lag that we didn't expect. And so that's the first issue. The second thing I was wrong about is when I said, I'll use a vendor to translate the audio just fine. I had always been under the impression that since auto captioning works, mediocrely, that speech to text was really a solved problem. It's not. Most transcription models that you see in the marketplace are built on wideband audio. So that's 16 kilohertz sampling rate audio. And that allows for a lot of richness and a lot of information that telephone audio doesn't, because telephone audio is limited to an 8 kilohertz sampling rate. This was a great decision for telephones because 90% of the sounds that actually make up language are encompassed in that 8 kilohertz band. The unfortunate thing for models is that some very important sounds aren't actually there. So like when you're on the phone, you can't actually hear, I believe it's F and S sounds, because they aren't encompassed in that band. Your brain is actually filling in those gaps for you, which is great because brains are great at that, but models are horrible at filling in the gaps where we don't give them data. So our out-of-the-box word error rates from almost every major speech transcription provider was almost 40%. And so word error rate is how you measure accuracy of speech recognition or speech to text. And it's basically saying, how many words did you get wrong? And there's all sorts of ways to say, if it shifts a little bit, how do you change that calculation? It can get very, very interesting and competitive and nasty. But by all metrics, the out-of-the-box word error rates for these models were about 40%, which means that our models, like our classification models, are only getting 60% of the information that they would have otherwise, because 40% is basically lost to garbage. And then we also thought that these models would serve all of our customers equally. However, when we looked at these vendor-provided models from, again, literally every big speech-to-text vendor, they all perform worse on women and worse on accented English. This is unacceptable because throughout America even, we have so many different accents. And T-Mobile in particular, we have a huge base in Georgia. We have a call center in Nashville. And these are areas of the United States with very distinct accents. And if we can't even get our call center representatives transcriptions good, how will we ever get the breadth of our customers good? And then we also thought that speed wouldn't be an issue, but we were having up to 5 seconds of lag between when a customer said something when we could see the transcription. That's quite far behind in a voice conversation. So out of the box models for telephone audio, they suck. It's not a solved problem. I was super wrong. I also thought that load would not be an issue. And so what I mean by that is, we're going from having 10% of the volume that exists in messaging, like 10% of the overall care volume, to having 100% of the care volume, which is 90% voice. And so the first issue is I thought that would scale linearly. So I thought the more, for each conversation each instance of our model could serve a certain number of conversations, and it wouldn't matter if they were in text or in voice. This isn't true because voice conversations are extremely long. You are more likely to meander, to talk about absolute nonsense, and text-based conversations are very, very, very business. So it turns out that when this is in production, the number of instances that we need for 10 times the traffic was actually 30 times the compute, which is, it's very expensive. And then there's lots of moments when you're on the phone where nobody's saying anything. Everyone's called into a call center and had somebody say, let me pull up the details on your account for you, and sat there for a good 2 minutes and 30 seconds in complete silence. We were paying people to transcribe silence. So the load as far as actual conversations increased, but so did the amount of work that our models were having to do, which was unanticipated, and it's extremely expensive. So we had a few strategies for how to cut the cost so that way we could still be viable. One, very easy, build a model to determine silence and don't transcribe silence. Another strategy to lower the model cost is that our classification models and our intent models, they are these big, beautiful neural network of neural networks, like extremely deep learning R models that are containerized. And so they are a little bit resource intensive because they are deep learning models. And so we created a low resource importance model that after an utterance is said, we determine whether or not we think that that is information dense enough to send to our classification model. The goal here being to filter out some of the small talk that happens in voice that doesn't happen in text to try and increase our overall model accuracy. And then we also toyed with running these models as Java services, which we just got working literally yesterday. And there's a blog in progress, and I'm really excited to talk about that when I finally can. But the final assumption I made, and this is the most ridiculous one, was that our models will work just fine. They don't. They are horrible. There are tons of things in casual speech that casual text does not have. So you have increased filler words. You have back channeling, which is like when you're talking and somebody says, yeah, So you have to deal with that. You have to deal with small talk as a concept, which really doesn't happen in business text. You have to deal with two different signal environments. So we can control what a call center sounds like, but I cannot control where a customer is calling us from. The first transcription that I had to do was a 20-minute call that took multiple days for me to transcribe because she had dogs barking in the background. If my human brain can't transcribe text, how could I expect a model to do it? And then even with perfectly human transcribed audio, our overall model accuracy for our intent dropped almost 20%. So even if the transcriptions were perfect, we would be losing 20% of our accuracy just because speech is that much different than text. And these errors compound when you think about all the transcription errors I was mentioning. So the transcription models we were spending a ton of money on were only 60% accurate and guarantee a 20% decrease in our accuracy. So now we're left with like some hot garbage to serve up. So I was wrong about literally everything that I thought would make this product easy. So what's next? And what's next is we keep building. We are working with open source platforms and building our own in-house models for speech to text, which is what I wanted to do from the very beginning. But by taking 60 days and stitching together all of these different technologies and tying them to our text stuff to build a prototype, we were able to secure enough funding to start up a team that is actually going to dig in and build these in-house voice models of my dreams. So we will have equitable voice models built on audio that serve all of our customers equally and are in our data centers, so that way they will be extremely fast. And we're going to also work on serving our models created in R as Java Spring Boot services, and then just refining the product vision for the voice space, because in messaging, our product was really focused on context switching. We had, a messaging agent might have 6 or 7 different windows open and they're popping back and forth between all these conversations. But in voice, you're focused on one person's issues. So our problem space becomes different, where we make our bread and butter in the voice space is by eliminating all that dead air. And so even though the results were horrible and all of my assumptions were ridiculous, we were able to prove that it worked enough to get millions and millions of dollars in funding to do what I really want to do, and it's create beautiful models in-house. And so in short, one does not simply lift and shift a text NLP product to streaming voice. And if you are looking to do that, I hope that I've illuminated some of the stumbling blocks that will very, very obviously be in your way, because it's not as straightforward as it seems. But even with all of that degradation, we were able to prove real value. And so the flip side of this is maybe sometimes it's really okay to buy a bad vendor product for a little while, if it gets you funding to build your own in the end. And with that, I would like to say thank you. Everything that I've learned in this entire project was really from a machine learning engineer on my team called Phoebe Parsons, who has a background in speech. So she was the person all around telling me, no, Heather, don't go into the weeds, pulling me back. But still, there were so many little assumptions that are made. You think that this is a simple technological problem that doesn't involve a lot of modeling. I thought we had already built the models, and it turns out I was wrong. We haven't already built the models. We have way more models to build now. With that, thank you. And if you want to talk to me, I'm extremely active on Twitter, but if you want like fast business responses, my work email is definitely the one to take. Thanks.